In our previous lesson, we discussed specific elements that were needed to be added to our instruction pipeline, such as buffers between each of the stages. And so now we'll talk more in detail about some of the data path components that additionally need to be added for our pipeline. And so we want to consider and keep in mind what occurs in each of the stages. In IF, we're going to be fetching instructions into the instruction register, and we have to increment the program counter. In our ID and RR stage, we're reading register contents. Our execution stage is going to either perform arithmetic logic or perform address computation. And with our memory stage, we're going to fetch and store the memory operand and be able to write to the register if needed. And so what we'll take into consideration appropriate data path elements that are needed in order to propagate the contents of our buffers between the stages appropriately. And so we need to make sure we have an understanding of which of our units are being utilized for each instruction stage. In our fetch, we're going to make use of the ALU, PC, and memory units. The IDRR is going to make use of our register file, our decode logic. Execution stage, we're going to make use of our ALU. In mem stage, we're going to make use of memory. In our write back, we're going to make use of our register file. And so with these in mind, we need to consider what components are needed for both IDRR and WB. We see that we're using a register file for both of those. And so what does that mean with regards to the new data path that we have to set? And so here we can depict the elements that we need as we transition between each of our stages, represented with our data path. For our fetch, we have our ALU, our program counter, and iMemory. For IDRR, we'll have a register file and appropriate decode logic. And then for our execution, we'll have our ALU again, memory components with DMEM, and write back we'll have our data that is written to our register file. And so it's important to analyze each of the components that we have throughout each stage, and we look at and see why we'll have a register file that needs to be made use for. And so does this mean that we'll need 2 register files? Because we're having one that needs to be used in our IDRR stage, and then we have another one that is going to be used in the write back. And so in order to make use of this, we can simply utilize our dual ported register file with appropriate addresses to accommodate both reading and writing at the same time. So we make use of the register file in 2 stages. And so with IDRR, we can use it to read parts such as the A address, the B address, and the A output and the B output. So for the write back, we can use it to write parts, the destination address and the input. So this allows us to share the register file on each clock cycle. So that means that the representation for our dual ported register file in both stages will use the same logic and consequentially will represent the same hardware unit that we'll utilize. And so we can illustrate how this would occur with instruction 4 being stored and then writing for instruction 1 occurring in the same cycle. And so now we need to take into consideration our buffers and how they are going to be used, and specifically what goes into the buffers, and for each stage, what is needed. And this is important because for different stages, we're going to need to propagate different information. And so let's consider going back to our sandwich analogy. So let's compare the instruction pipeline. So for our analysis for Bill's sandwich pipeline, what do the buffers between stages serve the same function as? Is it A, a partially assembled sandwich, B, an order form pass between stations, C, a combination of the above two, no comparison? What's a buffer? Or you're making us hungry again? And so we know that in the past, we've used it to represent a combination of the two. So what's going to make up the partially assembled data sandwich? We have the instruction register is going to represent the order form. And then the sandwich is the partial execution of the results. And so this makes us wonder, do the buffers have to all carry the same information, or can each buffer be different and specific based off of the information that is needed? And so this will lead us into having specific buffers that are used throughout the stages. We'll have an F buff, a D buff, an E buff, and an M buff. And so what do we need in each one of those stages for our buffer? So with the F buff, we're primarily going to need to represent the content, need to have the instructions read from memory. With our debuff, we're going to need to be able to decode the IR and values and read from the register file. Our ebuff is going to need to contain the results of our ALU operations and plus other parts of the instructions depending on the instruction specifics. Our mbuff is going to be essentially the same as our ebuff, but it depends on if it's a load or store. If it's a load, then what we need to do is have the buffer contain the contents of the memory locations that needs to be read. And so let's return to our previous non-pipeline macro state data path. And so at each point in this processor, the processor is only in one stage as we progress through the data path. And so with our pipeline approach, what macro state is a pipeline processor at any point in time? Is it going to be fetch? Is it going to be decode? Or is it going to be C, execute? Given that execute is normally a large portion of our pipeline, of our data path, or will it be all of the above? And the correct answer would be all of the above, because when we're in a steady state for a pipeline processor, we can have 5 instructions in different stages that are being processed in the pipeline. And so this allows for the processor to simultaneously do various computations, which represents that the pipeline is in various that the processor is at all stages of the pipeline, and allows for execution to occur in 5 cycles. And so let's consider the anatomy of an add instruction. And with the add, we're going to have our IF stage being in cycle 1, our IDRR stage being cycle 2, our execute stage in cycle 3, our memory stage in cycle 4, and our write stage in cycle 5. And so what actions need to occur during this process? During the IF stage, we need the instructions to be fetched from memory and placed in the F buffer. For our IDRR stage, we need to read register RY into our debuff. We need to read register RZ into our debuff. We need to copy the opcode from FBuff to debuff. We need to copy RX from FBuff into debuff. For our execute stage, we need to perform the appropriate addition. We will copy the opcode from debuff to ebuff. We'll copy RX from debuff to ebuff, and we're copying ebuff to mbuff in our memory stage. And then in our write back stage, we're going to write the result of addition into register X. And so how exactly could we quantify the sizes of the add instruction for the various buffers between the stages of the pipeline? What do we need to take into consideration in order to determine the size that would be needed? Well, we need to make sure that we're able to represent each component that we need at each stage, and how that is going to be represented in each buffer. And so what we can take into consideration is that we're going to have make use of a structure to represent each component that is needed. And so here we can see, going through each of the stages between the buffers, what's needed. And we have a structure that represents each buffer. So for FBuff, we can see what is needed in the values and the sizes. So for opcode, 4 bytes, our register X and register Y, a junk value of 16 bytes, as well as a Z register, 4 bytes. And this is for our instruction register. This is represented as a strut. And so for FBuff, we have a strut inside of a strut. For our debuffer, what do we need to represent is the opcode, our X register, our value for A, our value for B, and then also, and so that will represent what we contain in our debuffer. For ebuff, we have the opcode, register X, and a stored result value. And then for our mbuff, we'll have our opcode, our X register, and an appropriate result. And so how does this represented in our, as we progress through each stage? When we go to ID, the opcode is being read into our debuffer. RX is copied, and the values from RY and junk are read. And so this allows for us to step through to see what occurs at each stage of our pipeline as we progress through. And finally, we write the result back to our write register. And so what differences are needed for an add-I versus an add? And so with add-I, we have a little bit of different in that we have a need for an immediate field that is slightly different versus for our add. And so we're able to go through each of these steps to see what instructions are needed as we progress through. And the differences in our buffer structures for add-I and comparing to add. And so we've been able to take a look at how we would design the buffers for add-I and add. So how do we generalize the design of the pipeline register? So we can look at each instruction in the ISA and decide what needs to be carried over from one stage to the next with consideration to appropriate opcodes and other fields that need to occur. So if we were to design the debuff register for our LC2200 instruction set, we want to make sure that we don't optimize by overloading the different fields of the register. And we consequently need to decide what fields need to be in the debuff for each instruction in the instruction set architecture. And so let's take a look at what's needed for add and nan, add-I, BEQ, and so forth. And we can see all of the various components that are needed for each one. And so we want to identify any differences that might be present between each one. And so from there, what we need to do is take the union of everything that is needed. And this would represent the unified structure that we could use for our debuff implementation to denote all of the requirements that are needed. And so in the IDRR stage, we'll fill in the fields to commensurate with the instruction in FBuffIR. And so we'll leave unneeded fields unfilled. And so with that in mind, you can consider what fields would be needed if we wanted to fill in our JLR instruction as well. And so we have a common data path for our pipeline design structure that can be utilized to represent all components. And so this is important because we've been able to modularize the overall design, which means that we can take advantage and ensure that smaller modules are made use of with our pipeline registers to incrementally build components. And so if we consider for our JALR instruction, what fields in the debuff are not needed to be filled in? And so we know we'll need to place the value for the RX specifier. Do we need the contents of the program counter? Do we need the contents of RY? Do we need the contents of RX? Do we need an immediate value? Or is it both C and E, where we don't need the contents of RY and we don't need the immediate value? And so the correct answer would be F, that we don't need the contents of RY and we don't need the immediate value. We can put the value of RY into RX because that'll be passed down to our write back register. And so what are some considerations that we need to take into consideration for BEQ? What fields in debuffer would not be filled in? And do we need the contents of Y? Well, we'll have to fill the value of Y in. So do we need B? And we will have to fill the value of, we will have to have the value of RX and RY. Do we need the program counter? And we'll have to add to the program counter value. So do we need the immediate value to sign extend the immediate value? Or do we need RX specified? So RX and RY are going to be specific fields in the instruction based on how the instruction set architecture is designed. But we can use those for whatever reason. RX in this case isn't going to be a destination register. It's just providing a source register. So those are some appropriate considerations to keep in mind when reconstructing the data path for pipeline design. But these are just a few things to keep in mind. Next, we'll talk about appropriate pipeline hazards that we have to be aware of.